Hello everyone, welcome to my presentation. Today I'm going to talk about the effect of galvanizing on mechanical properties of high and ultra high strength steel tubes. Galvanizing. First of all, galvanizing is one of the best corrosion protection techniques and everybody knows about this technique. So basically we dip cleaned metals into molten zinc and we have a barrier against corrosive environments, and also we have a cathodic protection metal. So these are the steps for galvanizing: casting, cleaning, rinsing, pickling, rinsing, flux solution, drying, zinc bath, which is the most important one, and water quenching. So in step 7, metal parts are exposed to a high and elevated, or let's say elevated temperature. So we have different type of steel materials. We have ultra high strength steels with yield 960 and above, high strength steels from 450 to 960 MPa, and mild steel from actually below 450 and equal to 450. So the first one, ultra high strength steel, gains that strength from a special heat treatment technique. They call it direct quenching, or quench and tempering in different scenarios. So they are very actually sensitive to heat, and it is important to see if they are actually exposed to heat, how they change and how their behavior changes. So we have a lot of studies that they study the behavior of these type of steels, high and ultra high strength steels, after or during fire. For example, in a study by Azhari, you can see here that during fire, actually, by increasing the temperature, we have a decrease in material properties, and the same after being exposed to fire and cooled down, we lose some of our strength. For example, if you expose this type of steel to a 450 degree, the decrease in strength is from 1400 MPa to 1200 MPa, as you can see here. So it's important to see if your material is changing or not, and it's not just fire that is elevated temperature. In galvanizing, we expose these type of metals to a temperature of 450 to 500 degrees. The other important thing when it comes to galvanizing of these type of is that they are high in silicon. For example, as you can see here for UHSS, HSS, and mild steel, the silicon content is changing a lot, and it is important. As you can see here from this curve from ArcelorMittal, the silicon content is changing the thickness of coating a lot. For example, here, if the silicon content is above this value, you can see that a big coating thickness can form when they are dipped for 10 minutes in molten zinc. So the aim of my study was to find a technique for galvanizing these type of tubes. So what we did, we took some tubes, mild steel, high strength steel, and ultra high strength steel, as you can see here. Then we galvanized them having intact surface or sandblasted surface. Why did we sandblast the surface? We wanted to see if the actually rougher surface increases the interlock or shear connection between the coating and a steel substrate to work in our favor to form a robust coating. And then we changed the bath time to see how it's affecting the material properties and the coating. Then we conducted some tensile tests on the coupons cut from these tubes after galvanizing, and some compressive tests on short tubes before and after galvanizing. As you can see here, these are the failure modes for high strength steels, and these are failure modes for ultra high strength steels, which are at an angle, so it's a shear failure behavior. And these are the compressive local buckling failure mode of all tubes in. Here you can see the stress strain curve of ultra high strength steel tubes before and after galvanizing for different galvanizing duration. As you can see, we have a reduction in yield strength, but it is not much. It can be tolerated. So even after galvanizing the Arashpour ultra high strength steels, uh, we we can see that the transition from elastic to plastic is much faster, because actually galvanizing works like annealing, and it is working like a stress relieving the cold forming of these type of tubes. The same thing happened to high strength steels. You can see that the transition from elastic to plastic is changing drastically here, and it is becoming sharper, and we can see upper and lower yield points. Also, the ductility is increasing. We can see a little bit of reduction, but we can see the ductility is increasing, and actually this is working like a small heat treatment for these type of tubes. Also, you can see in mild steel, rather actually opposite to those tubes, the yield and ultimate strengths are increasing, but the behavior again is changing from a cold form behavior to a hot finish behavior, where you can see the upper and lower yield points, a flat yield plateau, and then a strain hardening. But unlike those two curves, the ductility is decreasing. Here you can see the compressive behavior of these tubes, and you can see that in compression, actually we didn't lose a lot of the capacity for ultra strength steel tubes, but again the transition from elastic to plastic is faster. Here we didn't see much difference between different tubes galvanized for different durations. So in compression, the galvanizing time is not changing much of the material properties. For high strength steels, the transition is actually sharper, so the stress relieving and heat treatment, pseudo heat treatment in a way of these galvanizing heat exposure worked. Then we conducted some experiments to see if the coating behavior of galvanizing coating is changing from after being sandblasted, or for different elevation, for different actually dipping time. As you can see here, we have different small tubes, and we have a small regular impact rig. So we conducted some impact tests on different tubes, and these are the results. As you can see, by decreasing the bath time, the coating is working better after impact. For example, for UHSS tubes, you can see that the coating is very brittle for a 6-minute bath time. But if we decrease the bath time, it is working better, and the coating is more robust. And this is because the coating thickness is much higher for 6-minute dipping. Then we conducted some hardness tests, and we measured the coating thickness using this alcometer device. These are the coating measurements, and we made a lot of measurements, and we actually did average these. So you can see here that by increasing the bath time, the coating thickness is increasing, and by sandblasting, the coating is shifting up, so the thickness is increasing in all bath times. So actually sandblasting was not a good option, and also it's better to keep the dipping time around 1.5 to 3 minutes to gain a good coating which is not thick and is not brittle. And we found that actually the hardness of materials for high strength steels did not change much, but for ultra high strength steels, after galvanizing for 10 minutes, the hardness dropped around 10. Then we conducted some bending tests on these beam shape specimens to a certain strain. So the strain was measured for all of them and did not go beyond that. Then we cut the bent region and the intact region for micrographic studies. These are the micrographs of UHSS tubes, and as you can see, the galvanizing has 3 layers, eta, zeta, and delta, and it increased the zeta layer by increasing the bath time. And that zeta layer is actually brittle and makes the coating brittle and not suitable. So it's better to keep the bath time shorter and not sandblast, because as you can see, by sandblasting, the coating thickness increase in zeta layer. The same thing happened in high strength steel coat tubes, as you can see here. So it's better to keep the bath time short and not sandblast. Then in the bent region, we counted all the cracks. We have two types of cracks, visible and embedded cracks. We found that more cracks formed on UHSS tubes and more cracks formed on blasted ones and more cracks formed on tubes which were galvanized for a longer time. And the visible cracks became higher for all of these. So UHSS, blasted, and more bath time, the visible cracks increased. And visible cracks are bad ones actually because they expose the steel substrate to corrosive environment. All in all, we need to understand that UHSS and HSS materials are prone to changes of material properties when exposed to heat. And galvanizing is heat. So we need to understand that if you're galvanizing these materials, you need to measure their behavior after galvanizing and use that in your design. Also, we found that to form a nice coating on these type of steels with high silicon content, one of the best solutions and easier and actually practical for big jobs is to keep the dipping time short. It cannot be kept below 3 minutes actually in practice because they need to skim the bath when they are dipping the actually metals into the bath before they can take them out, so they need a little time, but that can be achieved by this method. When they dip the metals into the bath, the workers or the machine, they right away can skim the bath to take the parts out. So they should be very fast, but it is actually tangible as we perform the same thing.